Hey guys, good evening, all of you from India. And we have with us Dr. Jyotishka Datta, and he has done his hi Jyotishka Datta, and he has done his B star MSAT from ISI, has a PhD in Purdue in statistics, and now he's an like professor of statistics in Virginia Tech. So I was talking to Jyotishka Datta about about how to give an idea about the penalized loss function. Okay, about how that idea of bias variance trade-off in our mathematical and statistical framework. And he suggested me this beautiful idea about the topic today. And without further ado, I will head over to the screen to Jyotishka Datta. Welcome to Chinta Statistics Analytics Department.
Okay. Hi, everyone. Firstly, thank you, Srijit, for putting this together. I have obviously I have given different research colloquiums at different points of time, and this is sort of a first for me as well, talking to younger students. So, what I'm going to do is. It's sort of an overview. So you can think of this as where your usual study of multiple linear regression linear model stops, and um, then you want to explore more of the methods for higher dimension. Okay, how do we modify the existing methods so that they are suitable for higher dimensional inference, right? And as we'll see in a few minutes that these are becoming more and more popular. The reason is that most of the modern experiments where you have very high throughput experiment, which means you collect data, you collect information on many predictors, many variables at the same time, and you want to put all of them in your model. Then this problem of finding the best possible model, the problem of finding the best possible subset, these problems become very important. And at the same time, you don't want to you don't want to do false discoveries, so you want to prevent misclassifications as well. So most of the methods that I'm going to talk about, I call them this very broad term, umbrella term, selection and shrinkage, as most of the goals for all of these methods can be classified broadly into selection, where you want to select what is relevant for your model, and shrinkage, where you want to shrink your estimates to the right amount so that they are suitable for high dimensional data. Okay? So here is a rough outline for the talk today. I'm going to give a very broad 10,000 feet overview of what has happened in this area from, I guess, late 1990s to today. So I'll start with a quick review of linear model. Then I'll start talking about model selection. I'll cover the methods that have been very popular, the Lasso and ridge regression, but slightly older. And then I'll talk about the more modern methods of concave versus convex penalty. Then part two is somewhat more advanced, more recent, and also more connected to my own research agenda, which is Bayesian shrinkage. So here we will take a sharp departure from the frequentist ideas of convex and concave penalty, and then say that, well, we can motivate some of these methods from a different Bayesian lens, and then argue that, well, you can have all of these properties and some more for these methods. And then we'll also establish that they are not really that different. There is some connections between the paradigm of penalized regression and this Bayesian shrinkage. And then again, I'll talk about some recent developments. Okay. All
Perfect.
right. And as I probably should have said at the very outset, please feel free to stop me at any point to ask any questions. This is an overview, and I think I'll much rather explain everything um, better than cover more topics. All right, so here is the first canonical example. This is very popular in the literature for large-scale inference. It's been part of many books and papers, especially by Professor Brad Efron. So this is a prostate cancer data. The idea is that you have 6,033 genes for 102 individuals, 50 of them are normal controls and 52 of them are patients. And the goal here is to identify the genes that are implicated for prostate cancer. So you want to identify genes that have a different expression level for the normal people and different expression level for the cancer patient. How do I do that? You can think of simple ideas from your undergraduate statistics. You can calculate the t statistics for every single gene, and then if you want, you can normalize this. You can look at the CDF of that test statistics and then apply the inverse Gaussian CDF transformation so that the test statistics are roughly normally distributed, right? Now the idea is that if I now plot all these z values, all the test statistics in a histogram, then you see this shape. And it suggests that there are some interesting genes. Why? Because if all of them were insignificant, if none of them had any effect whatsoever, then this histogram would perfectly match the solid line of the normal zero and density curve. But what you see is that there is a dip in the middle, and if you look at the tails, there are some genes that are higher than the tails. Those are the genes that are differentially expressed. So one problem here is that if I give you the list of if I give you the data for all the 6,000 genes and the 102 patients, how do I identify those that are different? So here is a problem that has the element of sparsity. There are obviously many genes, like here you have 6,000, but not all of them are important. Maybe a handful of them are important, and we want to identify them in a principled manner. This one is for, so here this example is continuous, and here is an example from discrete data. This is from one of the earlier projects that I was involved in. So what happens, what you see here is basically the x-axis are the amino acid positions on a chromosome, and the dots that you see, those are mutations, right? And what happens is, if you look at any chromosome, then there are some positions where you see lots and lots of mutations. Those are possibly sites where mutations converge, and then there are some sites where you don't have so many of them. Now, one of the key things in the study of rare mutation is to identify where do this happen, right? Obviously, if you look at this picture and you don't need any statistical methods to say that, well, I can see some of the bigger hotspots, right, where the mutations are converging. But what about the others? Can you identify what's the noise? How many mutations will you ignore if they are falling on a space, right? That's one. The other problem is it's not
Hello.
enough to just, yes, hello.
Yeah, I have a small question that can you just like explain the diagram once again? Like, what are this? What is the y-axis? The
Here,
second one,
okay.
huh? Figure
Yeah,
two.
so here the y-axis. So these are basically different individual mutations plotted. So you can
Okay.
think of you get data from a single cancer patient, and that person has mutations on the positions, maybe 100, 200, and 500. Then you'll put the dots there. So
Okay.
you can think of every dot as a single point mutation on a subject. And different
Okay.
colors
Okay.
are for different types of, it's not shown here probably, but different colors are for different types of mutations. Like there are a few different types of mutations. Some are, you know, some break the protein, some don't, and so on.
Okay. 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 Yeah. Perfect.
So first problem is that we want to identify where these mutations converge, and you can, if you look at this picture, you can probably guess that there is again this element of sparsity. Typically you look at very long sequences, and only a few places of these long sequences will have these convergent spots. And the second question is more interesting, which is it's not enough to look at where these hotspots occur, but also ask this question: are they harmful? Can they say anything about the survival probability of a cancer patient? Are they influenced by environmental factors, genetic factors, and so on? Right? So those are mostly genetic questions in genomic sciences. The idea is that the underlying theme here is sparsity, although the data that you observe here is strictly speaking not continuous but counts. You see the number of mutations on a position. Um, Now, all of this could be put into this framework of what is now called wide data. It used to be the term large p small n was more popular a while back. So this can come from many different applications. Could be document classification, could be genomics like the ones that you have just seen, or genome-wide association studies. And there is more. We have worked on studies from social sciences where you collect data from many different social markers, and that could also be high dimensional. Not as high dimensional as, say, genomic studies, but these problems are everywhere. Physics, for example, you can have high energy physics with the same type of problem. So, what's the idea here? The idea here is that you have many more features or predictors or covariates compared to the number of samples or the number of observation. Now, if you think of a typical statistical problem as think of the linear regression problem where you have an X matrix where you have the columns are your predictors and the rows are your observations, then this is the so-called large p small n problem. Now, no matter what application you're looking at, there are different types of linear model for depending on what you're trying to solve. For example, if you're doing classification, then you'd probably do a logistic or probability regression. If you're doing a survival analysis, you might do a Cox proportional hazard model. So these are all variants, but the point is that when p is much bigger than n, when you have thousands or millions of features, the standard approaches will not work for any of these problems. So what I'm going to do is talk about some of the main approaches for handling this very high dimensionality of the feature space. Okay, so sometimes this is also called this has been likened to finding needles in haystacks. So imagine this. So this is a cartoon diagram of what we are typically interested in. You have a y, like the skinny blue matrix, that's a vector, and you have an X matrix where you have many features but only a handful of samples. Okay, so if you look at this example, for example, in genomic studies, you can have 40,000 genes for 100 subjects, right? Now here you want to find these columns or these variables that are important for your method. It could be the genes that are important for a particular disease or something else, depending on the application. Okay, that's the main problem that we are going to attack. Okay, and I'm going to talk about the many different methods, the many different advancements that has happened over the last few years. So, quick review of multiple linear regression. I'm assuming that all of you, if not most, you know what is multiple linear regressions. I'll not belabor this point, but the main idea here is that think of the simple linear regression y equals x beta plus epsilon, and you know that if you try to calculate the estimate beta hat, the formula for beta hat is x transpose x inverse x transpose y. You can also think of this as uh, take the uh, take the response vector y and then projecting it onto the column space of the X matrix. They're the same thing. The important thing here is that what's the dimension of X transpose X? If your X matrix, going back here, if your X matrix has dimension n by p, then X transpose X will have dimension p by p, and if p is much larger than n, then this matrix will not be invertible because it's a low rank matrix and the least square solution does not exist. Okay. So that's the main point. That's the main reason why you cannot simply do linear regression for very high dimensional data. But before we go there, I just want to point out that when they are applicable, linear model has very distinct advantages. For example, it's very interpretable, it's quite flexible, and when they are possible, they often show very good predictive performance. Um, and even then, even in the smaller space where suppose we have maybe 50 or 100 variables, not really a very high dimension, even then the question is relevant. You will see that a linear model has this nature where if you add more variables into the mix, the the fit quality will generally improve, right? If you look at the R square for a model with more and more variables, the R square will gradually increase. And if you look at the residual sum of square, then the residual sum of square will generally decrease. But the point is that it's not always statistically significant. So even for smaller dimension, the question is important: which subset of the predictors is the most important? And obviously, as I said, as is the focus of this talk, sometimes P is very large, P is larger than N, and then we'll be finding needles in a haystack. So that brings us to this topic of so-called modern regression. And obviously, modern is a misnomer in the sense that a few years down the line, this will not be so modern. Anyhow, so what we have talked about so far is that if n is much larger than p, and if a true relationship is approximately linear, then the LAC, this is the least squares estimate, that will have low bias and also low variance, which is good because then if you're thinking about this in a supervised learning setup, it will perform really well on test data. If n is um, almost close to p, uh, same variables as the number of observations, then there it will still be possible, but there'll be lots of variability in your least squares fit. There'll be huge overfitting and poor prediction on the test data. If p is larger than n, then you don't have any LSC, the variance is infinite, and you cannot use least squares estimate at all. So the strategy here is that we will either constrain or shrink the estimated coefficient, by which we'll add a little bit of bias, but that added bias will have a huge benefit in that it will substantially reduce the variance of the overall estimate, which will decrease your test error and you'll get a better estimate. So here is the idea in a nutshell. When you think of this as a thought experiment, you have a y, right, your vector, and you have a x where you have only a few variables like here. Those are the signals. And if you're a model and you look at the error on the unseen test data, and then you keep padding that x matrix with noise variables, so all these orange colored these are the noise variables. So the point is that if you keep adding noise features that are not at all associated with the true response, then it will lead to a deterioration of the fitted model, and that will lead to an increased test error. However, if you add signals that are truly associated, then it will get better and better. Right? So our point is to uh, find out strategies, principled approaches, so that we can find these relevant columns of X that are signals and not noises. So the other, so that's the main reason why we do this, right? We want to still fit linear model like things, but we are dealing with higher dimension, so we want to do model selection, right? The uh, other reason why selection and shrinkage is important is called model interpretability. So here the idea is that, well, if you have many variables in your model, not all of them are obviously associated with your response, then um, a model with fewer variables is often more easily interpreted. So imagine a simple linear model with, say, five variables versus a model where you have 20 variables. The one with fewer variables is more interpretable, right? And the this is the sort of philosophical idea of Occam's razor, which basically says that if you can explain the same thing in a simpler fashion with a simpler model, then that is more preferable. So couple of benefits. One is we're looking at selection and shrinkage because they'll give you better test error, better predictive accuracy, especially for higher dimensional example, and also even for smaller dimension, they'll let you choose the best subset. And the other advantage, which is not always which might be a secondary advantage, is that you will also need model interpretability by selecting the best subset of the model. So there are three main approaches for doing this in classical literature, and these are not very recent. Some of them date back to a few years. So the first one is subset selection. Here, the idea is that you want to identify a subset of the p predictors that you believe to be related to the response variable. Then you fit a model on the reduced set of variables, right? The second one, and I'm going to spend a lot of time on this, is called shrinkage, where you fit a model involving all the p predictors that you have, but now you shrink all the coefficients towards zero. This is also called regularization or penalization, because the idea is that you are penalizing the coefficients, the overall size of the coefficients. Right? Now, depending on what type of shrinkage you perform, and we'll explain this in more details, sometimes the estimated coefficients can be exactly zero, so you'll also get a model selection by shrinkage. The third thing, and I'm not going to spend any time on this, but this is also an approach which is used sometimes, is what if you could project your higher dimensional predictors, higher dimensional covariates into a smaller dimensional space. Say you project them into an m-dimensional subspace where m is much uh, less than p. Then you pretend as if those m predictors are your original covariates, and you fit a linear regression model with them. The main problem with dimension reduction is that now you are not looking at the original covariates, but you're looking at something like linear combinations of those covariates, and they are not always meaningful. I mean, you cannot always um, interpret what is the linear combination of a bunch of um, social variables, a bunch of variables, a bunch of genes. Then they're not always as easily interpretable as the covariates themselves. All right. So how many? What the main problem when you look at the subset selection is that when you think about the subset selection, what's the brute force naive idea? The naive idea is that, well, if you have p predictors, then there should be 2 to the power p subsets, including the null subset, where none of the predictors are important, right? And then you can think, well, I can do a brute force where I fit my model to all these 2 to the power p different subsets of the predictors, and then compare the fit, and I take the best. Here, the main problem is that here the main problem is that when p goes large, 2 to the power p will increase exponentially, and some point this will be infeasible. So there are some alternatives, and I'll talk about some of them today. And these are called stepwise regression. Here, the idea is that instead of doing a 2 to the power p exponential search, we'll construct a sequence of p models where the number of variables could be increasing or decreasing, and then select the best of them. So that will reduce your complexity from something that is exponential to something that is at best quadratic. All right. So let me see. Okay. So there was a question about collinearity.
Collinearity, yeah, yeah, yeah.
Yeah, I'll come back to that when we talk about Lasso and Bayesian shrinkage. I have some answers for that, hopefully towards the end. All right. So the first method that is quite popular is called best subset selection, and it is what it says it is. It basically looks at all the possible subsets and looks for the best model, but there is a slight subtlety in that. The idea is that, like I said, if you keep adding more variables, then the R square will drop. Okay. Um, and as a result, if you compare different models with different number of variables, the R square is not an ideal metric. So what best subset algorithm does is that it will so you can think of this as an algorithmic procedure where you look at model sizes from 1 to p is the full size, and you consider all the possible models that has exactly k predictors, and then pick the best among them. That could have you can do that using the simple R square statistics, because all of these models are the same size, right? And then you keep track of which model was the best at each step, and you draw a line. But now you compare something else. You can compare adjusted R square or AIC or BIC or one of those methods that adjust a little bit for the model dimension. So this is called the best subset selection. And you can see that why this will have 2 to the power p complexity, because you are going to evaluate p to k models for kth step. If you add all of them up, then you'll eventually get the 2 to the power p term. Now, as I said, the first and main problem is that it is often very expensive computationally. So you have to fit 2 to the power p models, which is a lot. And also, even for a fixed k, if you think about the factorial term, p choose k could be really big for big p and k. So if you have 20 variables in your path and you are looking at models of size 10, 20 choose 10 is a big number. And as a result, when you search a very large model space, there are chances of overfitting, which means that you could fit a model that is not necessarily the best, or it fits the training data too closely, so your performance on test data could be poor. So the idea is that you can reduce your search space and thereby eliminate some of these problems. And this gives rise to these methods called forward selection, backward selection, and mixed selection. I'll try to explain them from an intuitive basis, and then sorry, a few pages. Sorry, I'll try to explain forward and backward selection through from an intuitive standpoint, and then try to explain why they work and why they don't. So what's forward selection? So imagine you have gone shopping, and the idea is that you'll pick the best one first, put that variable into your shopping bag, and then you look for the next best, then you put that one, and then you look for the next best and you put that one. But here, when you put something in your bag, you don't get rid of that effort. So once in, that variable will always stay in. So you start from a null model and you include variable one at a time, minimizing some criteria at each step. Backward selection is the exact opposite. You start from the full model, and then you find out which one is the worst predictor, which one has the smallest possible association. You chuck that out, and then you fit your model again with the remaining ones, and then again you ask the same question, which one is not important, and you leave that out. So these are called stepwise because you are not looking at all possible models. You are basically looking at a sequence of p models, one at each step, and you are asking if you can include one variable at a time, right? So these are the two main strategies. There is something called a mixed selection, which is a sort of hybrid between forward and backward. Here again, it's like you're starting from a null model. You include the variables at a time, minimize the residual sum of square. But when you grow your bag of model, if the p-value of some variable goes beyond the threshold, then you eliminate. So for example, you have gone from 3 to 4 to 5, and then when you reach the step 5, you see that, well, one of the variables that I had in my bag from the start, now it has been somewhat insignificant because maybe other variables have explained the same effect in a better way. Then you get rid of that model. So it's like a hybrid of both forward and backward.
Okay, so we
Now,
have a question over here.
yes,
Owen Birch, that does speak. Can you like see the comment?
yes, sure. Does picking the
Yeah.
best model based on your full data, then evaluating using cross-validation. Um, your testers have been seen by your model coefficients. No, so the idea of not really. So when you're doing cross-validation, and I think I might have a slide on that. So the idea is that you don't fit your model using using the left out part. Otherwise, it will be overfitting. So yeah, no. You can also do other things, like if you can use a validation set where you leave out a bunch of observations simply for evaluating your model. Okay, but the idea is that in general, no. So cross validation is perhaps one of the best ways to evaluate our model, especially for when you want to tune hyperparameters and so on.
Okay.
Okay.
Yeah.
When I go to cross validation, I'll touch on that question once again. So, what are the issues with this stepwise procedure? So first, again, whenever we talk about methods, we have to evaluate them in the light of higher dimensional feature space, right? For a smaller dimensional feature space, suppose when you have only a handful of variables, they're not so bad. They're actually quite useful, and they are used quite often, right? Now, think about a higher dimensional case. When you think about when P is much, much larger than N, forward selection can still be applied, right? Because what you're doing in forward selection, you start from the null model and you go step one by one. And the only caveat here is that you can only build models m naught with the null model m1 with one variable up to n minus 1 and stop there, because you cannot use the similar least squares ideas for models beyond the dimension n, right? But backward selection requires, so you start from the full model. So the backward selection requires that the number of samples is larger than the number of variables, so the full model cannot be fit. So in high dimensional feature space, backward selection is not even feasible. It's not viable. Forward selection still is, because it can fit a subsequence of the models. Not ideal, because you're not obviously going all the way up to MP, the model with P dimension, but it is still viable. Okay. The other issues, which are probably more um, uh, uh, important, is that so stepwise selections are greedy algorithms. So they are computationally more advantageous over best subset. They tend to do well in practice when they're feasible. They are not always guaranteed to find the best possible model. Okay, so let's see why is that. So I'll present a very short example on why that is the case. For the other main problem is that they are greedy algorithms. So forward will always, so once in, it will always stay in, and in backward, if a variable is out, it will always stay out. And the problem is that it could happen that your best model at step 1 is just the variable x1, but your best model at step 2 are the variables x2 and x3. But the forward selection model cannot, none of the forward or backward selection model cannot get this sequence, because they'll always build a nested sequence of models, and they're not necessarily the best model at each step. In higher dimensional, as I said, you cannot apply backward selection. And the other problem, which could be more serious, is that even if we think that both these methods will produce the same sequence of models when they are feasible, that's not true. They did not produce the same sequence of models, right? So if I apply a forward stepwise search, and if you apply a forward stepwise search on the same data, it could happen, because of strong dependence and other issues, that that they produce different sequences of models, and then it's left on the modeler to choose which one is the best. So here is a pathological example constructed to show this effect very quickly. So you have two variables, x1 and x2, and then you get a third one, x3, that is just a linear combination of x1 and x2, right? And then you regress y on, and then you get your y responses from x1 plus 2x2. And then you regress y on all these three variables. Now, if you look at this, if you had to choose just one variable, you'd probably pick x3, because it has information from both x1 and x2. But if you want to pick two variables, you might pick x1 and x2. So when you do forward selection, the first variable it will select will be x3, then it will add x2, and then the full model. But in backward, what happens? Starts with the full model, obviously. At step 2, it will get rid of x3, because x1 and x2 already has the information of that is already in x3. Which means if you stop at step 2, the model of size 2 in forward and backward don't match, and that could be a problem. Right? So hopefully I have been able to talk about the issues of stepwise selection, and when they're applicable, when they're not, and more importantly, I hopefully have convinced you that in high dimensional space, it's not always applicable.
Okay, so there's some question
Yes.
related to this, like
Yes, I
it's
can
asked,
I can
yeah.
see that. Yeah. Let me answer that. So does that mean stepwise selection versus best subset is similar to gradient descent versus matrix calculation for model solution. In both cases, you get good model, but may not be. Yes, that's exactly right. Yes. So, in fact, you can. Yeah, that's a very good analogy. So when you do gradient descent, you might get stuck in a local minima, right? And that's the same thing that happens with stepwise selection. You can get stuck in a local minima for your model fit whatever metric you use, and might not get to the global minima that's by the best subset. So that's a very good analogy. Yeah. So this is basically a nature of greedy algorithms, right? It's not and as you know from other sources, greedy algorithms are often used because they are computationally advantageous, not because they are globally optimal. All right, so this takes us to shrinkage methods. And so here the idea is that we are going to shrink the coefficients towards zero. And why is that a good idea? Because the idea is that that will introduce bias, obviously, because you take the least squares estimate that is unbiased and then you forcefully shrink some of them towards zero. It will lead to bias, but the same thing will decrease the variance quite a lot. And the idea is that if the reduction in variance is much larger, then it would decrease the test set error. There is also some Bayesian motivations to do this, which means you can come at the same model from a pure Bayesian standpoint, and hopefully I'll get to that at the end of this talk. All right, so the first method is called ridge regression, also popularly called Tikhonov regularization. This was popular for quite some time in literature. So what you do here is that you look at the RSS, the same RSS for that you minimize to get your least squares estimate, but now you add a penalty term. The penalty term this is called the shrinkage penalty. This is the L2 norm of beta, or summation of beta j square. The idea is that if this additional lambda parameter, this is a tuning parameter that modulates the amount of shrinkage. When the lambda is zero, you get back your original ridge regression. When your lambda is infinity, then you put such a huge penalty on this penalty term that all your estimates are shrunk towards zero. Okay, so it modulates how much you're going to shrink the coefficients towards zero, and obviously the optimal solution would be somewhere in between those two extreme points, right? Now, as you can probably see here, that unlike the least squares estimate here, here for ridge regression, you put a value of lambda and you get a solution. So you get a solution path, one solution for every value of the tuning parameter lambda. And then this is not obviously expensive than running a least squares regression to find a value of lambda that will minimize the test error. So think about the advantages. Think when we're doing best subset selection, or something like that, then you're looking at a very large model space, trying to explore an exponential, commutative, complex model space to find your best model. Here, even if you have to tune lambda, that is a scalar parameter, right? And that's good. That is reducing your complexity. All right. So what happens? So I said that the main idea is bias variance trade-off, and I'll try to explain with the picture, the plot on my left-hand side, lambda versus mean square error. So what is happening here? As I said, when you introduce bias, or when you shrink towards zero, you will introduce a little bit of bias. So here, if you look at the left-hand side of the plot, lambda is very small, bias is zero because that's like your least squares estimate, unbiased, right? You keep increasing lambda, right? At some point, you are going to introduce a little bit of bias in your model. So this black line is going up, that's the bias. The green line is variance. What happens when you introduce a little bit of bias? The variance starts falling off quite sharply, right? And if you look at the purple line here, that is the mean square error on test data. And because of this bias, and you know that the mean square can be written as a sum of bias and variance. So what happens is, as you reduce variance a lot more than you have increased bias, there is an optimal point for lambda where the mean square error is minimum, and this is significantly lower than what you had for lambda equals zero, which is the least squares estimate, or lambda equals infinity, which is the null model. And that is the advantage of using a regularized regression. Question?
There is no question till now, but yeah.
All right. So now ridge regression, it's a really good method and very popular for many purposes. Even in fact, for prediction, ridge is almost unbeatable. Now, the problem, not a problem, but a feature of the ridge regression is that it does not select variables. So all the estimated coefficients from ridge regression are going to be non-zero with probability 1. So you don't get model selection automatically. The idea that the method that does this is called Lasso, which is an acronym for least absolute shrinkage and selection operator. It's one of the most beautiful and clever acronyms in statistics. So what does Lasso do? Lasso changes the penalty function to an absolute value of the beta just. So it's the L1 norm of beta. So again, you have the RSS and you add a penalty term that is the L1 norm of beta. And as it turns out, ridge regression shrinks all the coefficients to a non-zero value, but Lasso shrinks some of the coefficients all the way to zero, which means you get two of this at the same time. You get a simultaneous shrinkage and selection at the same time, which means it is also, you can think of this as an alternative to the best subset selection or stepwise selection, because it gives you the model, model selection at the same time. So here is a um, quick demonstration of what that means when you look at Lasso and ridge regression. So if you look at these two plots, these are applied. This is taken from this book called ISLR, Introduction to Statistical Learning with R by James Hasty, Tipshrani, and Daniela Wheaton. And so what does this show? If you look at the top one, you see the four variables that are probably more important than the others. But if you look at the region near zero, you'll see a lot of very small pesky coefficients that are hovering in that region. None of them are actually zero. So if you want to select a model, you have to apply some kind of manual threshold, right? And you have to say that, well, I can say that, well, if the estimated coefficients are not beyond a particular value, then I'm going to not select them. Okay, and that is true for any value of lambda. And you also see that how the coefficients start from their original LSE values, but as you increase lambda, they are gradually shrunk towards zero. What happens for Lasso? In Lasso, when you shrink, they are shrunk all the way to zero, which means if we stop at some value of lambda away from zero, they're only going to get a handful of them estimated to be non-zero, and that is your selected optimal model. Okay, so you see how the ridge regression solution path and the Lasso solution paths is different, and that is the crux of model selection by Lasso.
So there's a question
There's a
that
question when Lasso and ridge regression coincide with each other. If lambda is zero or lambda is infinity, then they will coincide because you get either the least squares estimate or the null model. But in between, they should not. They do not coincide, because in one, like I said, in Lasso, some of the coefficients are shrunk towards zero, and in ridge, they're not shrunk towards zero. So, and also the solutions are quite different. If you look at the formula for the solutions. Right. Now, I have just explained, I've told you that I'm running out of time. So I've only told you that Lasso selects variable, but I've not explained why or how this selects a variable. How does it promote sparsity? So here is a rough idea. If you think of 2 points, one is just 1, 0, and the other point is 1 over square root 2 and 1 over square root 2. One of them is sparser in some sense, that like, you have a non-zero and zero, and the other one is dense, no non-zero points. If you think of looking at the L1 and L2 norm for both these points, it is obvious that for the dense point, the 1 over square root 2, 1 over square root 2, it is penalized more when you look at L1 norm versus L2 norm. So L2 does not really has no preference between sparse and dense solution. L1 often prefers a sparse solution. Okay, it's more clear when you look at a different alternative representation of Lasso and ridge regression. The idea here is that, well, if you look at the optimization problem here, where you minimize this whole thing, this is same as minimizing the RSS subject to the constraint of C beta j less than some value eta. This C beta j is basically our penalizer, right? You can think of different norms as different values of this C beta j. So for example, if you take the L1 norm, here this figure, that is your Lasso. If you take the L2 norm, that is your ridge. You can also choose other values of those different norms, and they'll lead to other different types of regularized regression. Okay. Now, so for ridge regression, you can think of this as minimizing the RSS subject to summation beta j square under a budget. Similarly, you can think of Lasso as minimizing the RSS subject to the norm under a budget. You can also think of the best subset in the same manner if we consider the L naught norm to be constrained under a budget. Okay. All right. Now, here is the famous picture to show why Lasso produces a sparse solution and not ridge regression. This is just two predictors. And obviously, the idea goes beyond two to many, many dimensional space. So if you look at the Lasso constraint, so here the ellipses are the RSS, the diamond, the filled diamond is your constraint region, the solid blue area. And here the idea is that you are trying to minimize the RSS while you want your beta to satisfy this constraint region. So you're trying to find an intersection point. Now, because Lasso has corners at each of these axes, the ellipse will often intersect the constraint region at an axis. But the ridge regression has no such thing. It's a smooth surface, no corners at each axis. So typically the coefficients will not equal to 0. And you can, now you have to, when you think of large dimensional space, you can think of, imagine this to be a higher dimensional diamond and higher dimensional sphere, and think of how the diamond will have corners at each axis, and why that is, well, that will probably produce a sparser solution. Okay, so the other type of explanation that we often give is looking at the very special case where you put x equals I, so if your p is equal to n, and you reduce your problem to one that is often called a sequence model or sparse normal means. So you have just yi is not just beta I plus epsilon I. We look at this model because the general model where you have y equals x beta plus epsilon, the Lasso solution is not so straightforward, not so analytically simple as this one. Now, if you look at the, even if you look at this case and try to look at the solution for ridge and Lasso, what happens to ridge? Ridge regression solution, the estimate is simply a rescaled version of your LSE, the yj, right? It's just yj over 1 plus lambda. Something similar happens when you look at the full regression model. What happens to Lasso? Lasso is saying, well, if y is small, then it's probably a noise and I'll shrink it to 0. If it's beyond a value given by lambda, so if lambda is larger, then this region will become larger and larger. Then I'll shrink the LSE by a constant amount. So think of this implication. What is happening here is that for some of these beta j's will be shrunk all the way to 0 if the corresponding yj will fall inside that window. Beyond that, it will not shrink. But ridge will never shrink. As long as your yj is non-zero, beta j is also going to be non-zero. So here is how they look like, the shrinkage profiles. So the ridge regression will, it's like you take the input and you tilt them all by the same amount, and that's your output, this dashed red line. For Lasso, it is quite different. If the input is small, input is your x-axis. If the input is small, then you're shrinking all the way to 0. If it's large, then you add a little bit of bias to it. And the base subset, this is very important. If you look at the base subset, what it is doing, it's basically saying I'll shrink to 0 when inside an interval, and beyond that, I'll go back to the diagonal line, which is the output, which means if your yj is really large, so here, if your yj is really large, maybe then it's a signal, and I don't need to shrink at all. Okay, and we'll see that if I have time to cover some of those modern methods, you'll see how the modern methods try to be very close to this base subset selection. All right. Now, there are other variants of Lasso. So one that is very popular is called Elastic Net. The idea here is that Elastic Net performs group selection. So in Lasso, if you have a group of variables that are highly correlated, it tends to select one of them, ignore the others. So what ElasticNet does is it produces. The idea is that you look at a hybrid of uh, the Lasso and ridge regression, but as a result of this sort of hybrid penalty, you do you perform group selection. Okay, so this is how the elastic net penalty looks like. It's like inscribed with the between a circle that is ridge and the diamond that is lasso. Right? Okay, now lasso is quite old, right? It was proposed in 1996 by SD and Dipshirani, and over the next 20 or so years, there's been lot of developments, and these are many of the variants of lasso for different things. For example, the grouped lasso will perform group selection, the graphical lasso will perform graphical selection, and there are some of the modern methods that are that don't even look at convex penalty but look at concave penalties. Okay. So now I'll probably end after a few slides here. So what's the point between convex and concave penalty? In convex penalty, there are some advantages, like you get a unique solution and the computation is efficient. Theory is quite straightforward, but the problems are that there's often a poor estimation error. It tends to select a denser model, and you need very strong assumption on the design matrix. So there is a question about how collinearity or correlation affects this sort of methods. Here is a very general answer. The concave penalties are suffer uh, to a lower degree because of high correlation compared to the convex penalties like Lasso. Okay. The ideal is, of course, L naught, the best subset, which is NP hard, and we don't consider that. Non-convex penalties, sparser model need weaker dependence and also need lower signal to noise ratio, but they're also harder to fit. Right? So that takes us to this topic of Bayesian duality. I think I'll just skim the surface of what Bayesian duality is and stop there, um, and not talk a lot about this new age method. So what's the main idea? Think of the penalized regression scheme here. So you have a likelihood, right? And you have a penalty term. That's the most general form. If you are looking at the regression model, if your y is normal with mean x beta, then this log likelihood is simply your RSS, and this penalty is, in the case of Lasso, this is just the lambda times L1 norm of beta. Right. Now we can think of this in a Bayesian hierarchical setup where you think of this, if you look at the exponentiated version of the log likelihood or the negative log likelihood, you get the probability density, the likelihood for the data given your parameter. And you can think of this penalty, if you look at the exponentiated version of the negative penalty, whatever that is, it could be a prior on this parameter space theta. Okay, so that is the duality between Bayesian hierarchical models and the penalized regression. And as it turns out, if you think about the term e to the power minus lambda summation beta square, then it is like taking the product of a bunch of Gaussians with scale parameter lambda that are put on the parameter, each individual parameter beta j. Similarly, if you think of, so here is the idea. If you put normal price on beta, then the mode of the posterior distribution will be identical to your ridge regression. If you put a Laplace prior on each beta, then the mode of the posterior distribution is your Lasso solution. Right? And you can show that that was pointed out by the Lasso paper that, well, you can think of Lasso as a Bayesian version where you put a Laplace prior. The Bayesian Lasso needs something else. It says that you also need to condition on the error variance sigma square, otherwise you'll get a bimodal posterior distribution. But the point is that that you can put different priors on the beta on the parameters beta, and different priors shrink the coefficients to different amount depending on how much mass this prior density puts near zero. So for example, if a Laplace prior puts more mass near zero and has this singularity, then it will lead to a sparser solution compared to a normal distribution or a Cauchy that put lower mass at zero. Okay. Um, Now I'm going to skip a few things. Now the idea, the modern Bayesian methods that have been proposed for the last, I would say, 10 years or 12 years, is that, well, this could be insufficient shrinkage, right? So there is a few paper that shows that the Bayesian lasso, like the frequentist counterpart, has some problems. It might overshrink the large signal. So remember the plot where the lasso solution had a gap even for the larger y values. So that is overshrinkage. And they also don't work really well for when the design matrix, the X matrix, has very high correlation and the uncertainty quantification is not really good. So that leads to a lot of this new age Bayesian method. So the idea here is you can think of this in this way that, well, I'm trying to design a prior. So you had Lasso, you had rigid regression from Laplace and normal prior, but now it says that, well, if I can build a prior that has an infinite mass at zero and yet very heavy tails, maybe heavier than normal or Laplace, then such a prior might do better than Bayesian Lasso or Bayesian Ridge. And the answer is yes. This sort of prior is called in literature the Horseshoe Player, that was proposed sometimes in 2010, and it has gained a lot of popularity. We can show that it outperforms Lasso for sparser problems, but the idea is here the main idea is that it can directly model the posterior inclusion probabilities. So what is posterior inclusion probability? It's the probability that a beta j is non-zero given y. And the advantage of modeling that is that if you get an estimate of these inclusion probabilities, then you can simply threshold them. If the probability is high, then you say that the parameter is non-zero. Otherwise, you say the parameter is zero. Okay. I'll skip a few things and just show you one more plot and then
Okay,
stop.
I have one question, personal
Yes.
question, is that for sparse signals,
Hmm.
why, like, what is the, and can you explain what is the problem using Lasso? Like, what are the usual problems Lasso like
So yeah,
gives?
so this is one this is a plot that probably will explain answer that question. So if you look at this plot, what you see here is the shrinkage profile. If you look at the right side of the slide, um, so when your input is small, Lasso and most of the other methods will shrink very well. That's good, except for maybe ridge regression and the least squares estimate. However, if you look at uh, a larger value of the input where you should not ideally shrink at all, then Lasso will still keep shrinking. That is the over shrinkage in the tails, right? So, put simply, if you think of the posterior mean of beta j, then it should be equal to yj if your yj is really large for a normal means model, but it does not happen for Lasso. There is a non-vanishing bias on both the tails. But there are methods that don't do that. For example, it's probably difficult to see here, but there is this method called MCP. It's a frequentist method, minimum concave penalty. So instead of a convex penalty, it puts a convex instead of a convex penalty, it puts a concave penalty. And the idea is that if you look at the path, it shrinks near zero, right? But as you increase your signal strength, the shrinkage profile will come back to the diagonal line. So it won't shrink at all. And it turns out that the same thing is true for this sort of horseshoe priors, where you shrink very well near zero, but as you go away from zero farther, it does not shrink at all.
Perfect. Okay, okay, okay. So here is some question people are asking that I don't know what is that y is large coefficient. I don't understand the question. Shobit is asking what is input in this graph. What do you mean
Uh,
by input, Shobit? I don't know.
which here input. Okay, yeah, I can explain that. So think of the simple model where you have yj is normal with mean beta j and variance sigma square, right? Then your input is your data y, and your output is the estimate beta hat j. Okay, I think this is probably going to be my last slide, and then I'm going to stop. So remember how I said that difference in constraint region explains a lot of why different price shrink to different amount. And we said that, well, ridge is circular, smooth. Lasso has a diamond-like shape, more corners, and it will shrink more. It will be lead to more sparsity, inducing estimates. What happens to horseshoe? Horseshoe penalty, horseshoe constraint region, if you look at the equivalent penalty, that will look like the extreme right-hand side of my figure. Obviously, more sharp edges, and the probability that you will touch some of these points that are not on the axis is even lower than Lasso. So it leads to a sparser estimate. All right, so I skipped some of the earlier slides on this set of priors, but there is a lot of development on this, and the general family is called a global local shrinkage prior. The idea here is that that you design this Bayesian priors in a way that there is a global shrinkage parameter that will adjust to sparsity, but there is also a local shrinkage parameter that will help you identify what are the signals. And you can see that from 2010 to very recent past, there's been a lot of development in this area, producing new priors for different properties. Some of them are my own work, where you can show that, well, you take horseshoe, but then you have these other properties, or you modify them for a counter application, and so on. So lots of recent developments in this area. This in particular, the high dimensional inference, where you have a sparsity, is very, very popular. And if you're looking for new research problems in this area, this is a very, very hot area and has many applications. I think there is a lot of development on continuous case, where the simple regression type problems, but there are so many things beyond the simple regression. And we don't have full answers for all of them yet, especially from the Bayesian lens. So, for example, we looked at this simple problem with quasi-sparse count data, where your parameters are probably the rate parameters for a Poisson distribution. And it turns out that you need to construct a different type of sparsity prior for that application. Okay. So lots of development on that. And I'll end with this simple message that shrinkage prior for structured data is still an underexplored area. Similarly, penalized regression from a frequentist paradigm for structured sparse data is still a very underexplored and very hot area. And there are many, many unanswered questions. For example, dependence. We only know some of them. Like if there's a group dependence, we know that some of the methods work really well. But to capture dependence in a meaningful way and not have a deterioration of performance is still a very much an open issue. Okay, so I'll end with that. Here is some papers that you can that I'll encourage you to read. In particular, there is a paper a couple of years back that you wrote on Lasso meets Horseshoe. It's a survey paper review covering different aspects of both frequentist and Bayesian paradigm for this sparsity and high dimensional inference. By all means, please read that and comment. These are a lot of this my wonderful collaborators that I've worked with in the past, and thank you.
Yeah, thank you so much. There's a question I will just I have I will end with some thoughts, and before that, Shobit is asking, can you just see the question once? Yeah.
Okay. So I'll repeat the question. It says horseshoe, etc. seem very symmetrical. Is there any research on constructing your own penalty that is not symmetric but looks at the correlation matrix in X so that the correlated variables have interaction? A very good question. Yes, there are. For different contexts, though. So let me go back a few slides. So one of the things that we worked on very recently is this new prior called group inverse gamma. So here you have symmetry in each axis, but if you look at the joint induced density of all these priors, then you prefer that, well, you're looking at grouped variable where some groups are important, some groups are not, And maybe within each group, some variables are important and some are not. And then you depart from that. But more importantly, if there are, suppose you have very good knowledge of what is the dependence matrix. Sometimes you don't. You are looking at, you just have your data, but you don't know what is the unknown sigma matrix. But suppose you get a really good estimate of that, or you have some idea about what that is, then there are some new priors. There is one called spatial horseshoe, where they incorporate that dependence structure inside your prior. So it's no longer symmetric, but it can outperform the non-dependent or agnostic horseshoe when there is indeed a strong dependence. It's a really good question, and I think there's a lot to be done in that area.
Yeah, thank
Okay.
you.
Other
There was
question?
another, yeah, there was another question you told that we will be addressing that towards the end. Is like about collinearity in white data.
Yep. Let me see if I can have. See if I can show a simple plot here. No. So give me 1 second. Yeah. So I probably went over this too fast, but the general idea is that when you have a concave penalty uh, penalization methods with a concave penalty are depend not as strongly on these dependence conditions. So what I say here as coherence or irrepresentability, that is basically different ways of measuring the dependence between columns of your X matrix, right? So convex penalties suffer more for collinearity in your data. Concave penalties do not suffer as much, but that's a very overtly simplistic answer. What do we mean by collinearity? If there is very strong collinearity to the point of, at some point, if they're almost like linear combinations of each other, then obviously then you have a matrix that has a very poor conditioned matrix, right? And then all methods suffer. So agnostic methods can only do so well without having an idea about how strong that dependence is. We can show, because of the convex concave pool, that the concave methods or the Bayesian methods that lead to concave penalties, they suffer much less than the original Lasso and the set of convex penalty methods. Okay.
Okay. Yeah. So we have another question from Shoham Ghosh. Yeah. So he's
Hi,
asking
Shoham.
this.
In order to pool information within groups, is it sensible to use hierarchical shrinkage prior to adopt different shrinkage for different coefficients? And yes, that's exactly what is done. Well, so what is group lasso? So what group lasso does is, like, you put you know what lasso is by, and then what group lasso does is it basically says that, oh well, let me put like a different lasso penalty on each group. Suppose you have G different groups, then you separate those coefficients and then you put individual lasso penalties, right? And then people said, well, what do we need in group selection? Is it just that we need which groups are relevant, and then we also have a bi-level selection problem? So one level of sparsity is that there are many groups, only a few of them are significant, and then inside each group you have some variables, but not all of them are significant or not important, right? And the Bayesian methods do the same thing. You put penalties that will have a group shrinkage parameter or a grouping structure that will explicitly account for the grouped covariate. Okay. I should also say here that all these methods assume that the grouping structure is known, so you know which covariates are, in which groups and so on, and that's often true. The applications that you look at, like environmental data, where you have all these pollutants in your environment, but there are metals, there are phthalates, and there are pollutants with sulfur components, and they form natural groups, right? So and you want to select them or deselect them at the same time. So that's the rough answer. If for very unknown grouping structure, it's a probably more difficult problem.
Yeah, perfect. So yeah, so this idea of Bayesian duality is really interesting. Like it opens up the new ways of thinking about this penalty terms. I guess I hope this was the message to this undergraduate people over here. Yeah.
Thank you.
Uh, okay, there are other questions coming up. Shobit is asking like on with the
What
similarities between shrinkage and
similarities between shrinkage and partial pooling? Um, well, yeah, there are similarities, um, but I don't know of any. I cannot, on top of my head, I don't know of any like way to mathematically equate the two. But yes, yeah, there are obviously similarities because also in partial pooling you have the same bias variance trade-off kicking in. There's a question by Owen Barch and Shobit. We can obviously get in touch later to uh, clarify that if needed. So Owen has asked a question for data where there are repeated measures in linear regression. You may want to use a different estimate of the standard error, right? Yes. Are there parallels for this in shrinkage models? Yes, there are. For example, when you have okay, so one thing that I've not really talked about is how we handle the sigma. We sort of said that, well, I'm going to focus on only the mean parameter beta and ignore sigma as if it's a nuisance parameter. But when you get into problems like repeated measures or multi-level problems, then these are more important. And I think what people usually do is they build a hierarchical model that explicitly takes care of the repeated measure as opposed to naively applying horseshoe on repeated measures without taking that into account. Yeah, but yes, it is important.
perfect. Okay.
Yeah.
Okay. Any other questions, guys?
And just to make sure, so my I don't know if it shows on the maybe on the first page. So here is my email. Oh, it's not here. My email ID is my first name at vt dot
Okay, I will write
vt
it down.
for
Can you just
yeah, it's actually I can write it down here. I can post a
yeah,
comment, right?
yeah.
So my
Yeah.
email ID is jyotishka at vt.edu. If you have any questions where my answer was not sufficient, please feel free to email me. This happens to be my area of research, and I'm more than happy to talk with anybody about anything. And thank you all for these very stimulating and insightful questions.
Yeah,
Thank you.
thank you all of you for that. Yeah, thank you. I hope there are no other questions. You can always drop a mail to Jyotishka Datta, and yeah, and you can start an interesting conversation with him. Yep. Thank you guys, and have
Thank you
a
once
good
again.
day and a good night ahead. And yep, bye bye. Bye. Yeah.